In this video I'm going to explain about the single phase half wave R load rectifier. Now the circuit diagram shown here, okay, this is the one, is the single phase R load half wave rectifier. Now here I'm talking about the uncontrolled rectifier. Now when we say about the rectifier, we have two types, okay, two primary types, the controlled and uncontrolled. Now if we are using the switches, power electronic switch like thyristor and other the one which we can give the gate signals, so that one we can control the output voltage, so we call this one as the controlled rectifier. But in case of the diode, we cannot control the output voltage, so we call this one as uncontrolled rectifier. Now here our diode, okay, power diode is connected in series with the input voltage Vs. So Vs is the AC signal, Vm sin omega t. Again that one is connected in series with the load. Now here in the figure at the right, I have shown the that input waveform. So this one is Vs. The Vs is the input waveform. Now it is sinusoidal. And now let's check the output voltage. Now this one is your first part. This is the positive cycle. Here from 0 to pi is positive cycle, pi to 2 pi is negative cycle, again from 2 pi to 3 pi is positive cycle, and 3 pi to 4 pi it is negative cycle, and it goes on. And during the positive cycle, okay, during the positive half cycle, that is from 0 to pi, your diode will be in the forward bias, meaning you will have the plus here and your ground will be negative, and during that time your anode is connected to the positive, anode of the diode is connected to the positive, and cathode to the negative. So during that time your diode will act as a short circuit. And you will have the output voltage across the load RL, and that magnitude of the voltage will be same as the input voltage for that particular cycle. So this is our positive half cycle, okay, positive half cycle, which is given at the output side. And for the negative half cycle, so we are going to analyze for the negative half cycle. For the negative half cycle, you will have minus here and this one as plus. So during that time your diode will be reverse bias, okay, which means your anode is connected with the negative and cathode is connected with the positive. So during that time no conduction will take place, so your output waveform at the load that is from pi to 2 pi will be 0. And then again for the second positive half cycle you can expect the same waveform. The reason is, again, this one will be positive and other side will be negative, so we can expect the positive half cycle here again. And then for the next negative half cycle, again our output voltage at the RL will be, across the RL will be 0, and then it goes on. And then when it comes to the output voltage, since we are talking about the R load, so it is very easy to calculate the I using the Ohm's law. It will be Vs divided by R. Here if you replace with the Vs, it is Vm sin omega t divided by R. So when Vs is having some magnitude, you can also expect some magnitude from 0 to pi. And then when Vs is equal to 0, your I naught will be also equal to 0. So which is more or less is open circuit. Your diode is not conducting. So you will have 0, and then again from the 2 pi to 3 pi you can expect some magnitude here, and then again 0, and then it goes on, okay. So this is the output current. And then let's try to calculate the voltage, okay, voltage across the diode Vd. Now in the positive half cycle, your diode is acting as a short circuit. Your diode is acting as a short circuit, which means from 0 to pi is going to be 0. Your diode magnitude will be 0. And then during the negative half cycle, okay, during the negative half cycle, you will have this one as like it's reverse bias. So this is going to be open circuit, and whatever the output input voltage that we have has to transfer to that diode Vd. So it will be in the negative half cycle like the negative part, okay, 2 pi, and then from 2 pi to 3 pi again it will be 0, and then from 3 pi to 4 pi you'll have the magnitude across the diode. And the important thing that we have to calculate from the this rectifier is, since rectifier is rectifying the AC input signal to DC signal, so we have to calculate what is the average value of this output voltage. So V DC average, okay, average output voltage will be equal to, now here in order to calculate the average we have to find the integration, okay, we have to use the average. Now there are different methods to calculate the average, but in this case, so we are used to with the integration technique. So it will be 1 by the time period, 1 by time period integral 0 to t the input voltage, that is Vs, okay, Vs d omega t. Now here you have to substitute Vs with the Vm sin omega t. Now our time period t is 2 pi, and then in case of the half wave rectifier, uncontrolled half wave rectifier, your final VDC will be 1 by 2 pi integral 0 to pi, okay. Why I am taking 0 to pi? Because from 0 to pi we have got some magnitude, so this one will be Vm sin omega t. We have to integrate with respect to d omega t, and then actually there should be from pi to 2 pi again we have to integrate if there's any magnitude, but we don't have any. Here it is 0. Anything when you multiply with 0 we will be getting 0. So this is the expression to calculate the VDC. And then from here you can also calculate the current IDC, because IDC and VDC are related. So IDC will be equal to VDC divided by R. So whatever the answer, that solution we got here, can be substituted or can be divided by R. So we will get our output DC current. And then there's also we also have to calculate the RMS output voltage. So your RMS output voltage, okay, I'm erasing this one. Okay, oh, it's going okay. Wait for a minute, okay. Okay, now our V output voltage of RMS, okay, root mean square value is given by the root of, okay, root of 1 by t 0 to t V output, okay, that's the output voltage that we got, VDC square omega t d omega t, okay. This one we have to calculate under the root. So these are the that the performance index that we calculate for the half wave uncontrolled